All right, here we go. We changed it to a different edition of the textbook. This is the 9th edition of the Blumen's text, and so what happened was that we had, I've been using some older videos and that used a different table E, and I'll explain what table E is here shortly. And so what I wanted to do is I wanted to go ahead and record some fresh videos that really correlate directly with the problems that you work in and table E and so forth. So what we have here is chapter 6. In chapter 6 we're going to cover normal distributions and section 6.1, and then the applications in section 6.2, and those are directly related. So basically in 6.1 it's problems where there's just straightforward. In section 6.2 they're word problems. I'll have some sample videos from both. All right, so some of the learning objectives, we're going to look at the properties of the normal distribution, and that's what this video will address, so we'll go ahead and just stop right there. So, looking at properties of the normal distribution. Many continuous variables have distributions that are bell-shaped, and they're called normal distributions. So there we go. There's that language. And so right now what I want you guys to start thinking about is this bell-shaped curve, kind of like when you're in high school and your science teacher might have curved on or graded your test on a curve. And so that was the bell curve. This is what we're talking about. Sometimes it is called the bell curve. The gentleman that discovered this or established this was called Gaussian. And so sometimes they call it the Gaussian distribution. So just different names. The shape and the position of the normal distribution curve depend on two parameters, and those parameters are the mean and the standard deviation. And so as we look at our normal distribution here, what we see is that right smack in the middle, that value right there is going to be your mean. Remember that symbol mu? Mu stands for mean. So remember that's the population symbol, and that stands for mean. So my mu would be there. And then I have my standard deviations, and this is an approximate sketch. So this would be +1 standard deviation. Remember once again that symbol right there means standard deviation. And then we go up a little bit more, and that's +2 standard deviations, and we go up a little bit more, and that's +3 standard deviations. And if we go down, it's the same process. That would be -1 standard deviation, -2 standard deviations, and -3 standard deviations. And so to be able to discuss this thing called the normal distribution curve, we have two parameters. Remember, parameters are the data that we collect, the data that we calculate, and that's from previous chapters. You look up that word parameter. And so we need the mean and the standard deviation. Each normally distributed variable has its own normal distribution curve. Okay, that's confusing. So let's bump ahead to the next slide. So here's what we're talking about. So we have two sets of data here. We have data set 1 and data set 2. So we'll call it D1 and D2. D1, let's say, is the blue graph. And D2, let's say, is the brown graph. And so what you see is that in D1, the mean is 0, but the standard deviation is 2. So every data set or every variable that we measure is going to have different means and different standard deviations. Now, you might get a data set that has exactly the same mean and standard deviation, but it's unusual. So what they're trying to say here in this sentence is each normally distributed variable had its own normal distribution curve. Brown and blue. Each normal distribution curve has its own unique situation. That is, whoops, I'm the wrong way. Each variable has its own normal distribution curve. So wait, variable, what do they mean by variable? Okay, so let's just say that we compare the height of people in Albany with the height of people in Thomasville. So let's call this one Albany, and let's call this one T-ville. Okay, and so what we're saying here is we're saying that these two towns have exactly the same average height. their average height is exactly the same, but their standard deviation, which is also known as the spread, is different. So how spread out the data is different. And then, you might have a situation like this where, you have completely different means. So this guy has a mean of 0, this guy has a mean of 2. It moves it completely differently, but you'll notice that their standard deviation, which is also, remember, known as the spread, how spread out it is exactly the same. So the normal distribution curves, the actual curve itself, looks exactly the same, but they're in two different spots because their means are different. All right, so then we got these things called the properties. We've got our properties of the normal distribution. All right, so the properties of the normal distribution, let's just kind of blow through these. So the property is it's bell-shaped. So if you have a normal distribution, when you look at that distribution, whether it's in a line plot, whether it's in a histogram, whatever, it's going to have a bell shape to it. Inside of that bell shape, the perfect, let me make sure you understand this, the perfect normal distribution. Now this is not all of them, because we might have, and you'll see later on, the perfect normal distribution right smack in the middle right there would be your mean, your median, and your mode. It would be your average, it would be the one in the middle, and it would be the one that happens the most. It would happen right smack at the same spot. It's unimodal. Uni meaning one. It has one mode. So it's not a camel. It's not this one. It's not okay? It's not that. It's unimodal. It's this one. The curve is symmetrical. Well, symmetrical means you can fold it in half. Symmetrical means that when I fold it in half, I would get 50% on this side and 50% on that side. So we have that vertical line, that mean, median, mode right smack in the middle. We fold that guy in half. It's symmetrical on both sides. It's continuous. So when I start this graph, it goes on and continues into the other side. Don't sweat that one, a big deal there. It's not going to be like some crazy situation. They're just saying that you can't have breaks in it. Okay, it's just a definition. It's a property. The curve never touches the x-axis. Once again, don't stress on this one. It's not like a groundbreaking one. This is a property. If someone asks you about the properties, you have to understand that this is one of the properties. So just realize that the idea is that if you had an x-axis, or the x-axis is right there, and you draw your normal distribution curve, it's going to come up, it's going to come down, it's symmetrical, and it will get increasingly closer to that x-axis, but it'll never touch. It'll never actually get down and touch. It'll just keep getting smaller and smaller and smaller. The most important property that we have for this guy, there's two of them, and it's on this page right here. The most important property is this. If we take our normal distribution curve and we go from here, which would be like saying 0%, so that if you start on the left-hand side, that means there's nothing here to the left, and you go all the way to the other side, that is 100%. That's 100% of the data. That means that if my sample that I collected had 75 people in it, those 75 people would be distributed somewhere throughout this curve. They would have a location on this curve. The story I always tell is the story about the Iowa Test of Basic Skills. When you were younger and you used to take the Iowa Test of Basic Skills or any other standardized test, you get the score back. And it would tell you that you were in the 70, let's not use that number, that you were in the 80th percentile. What they meant by that is that you scored better than 80%. So if I drew a curve right here and I said that spot was right there, that's the 80th percentile, that means that you scored better than 80% of the people. That also means that 20% of the people scored better than you did. So there was 20% of the population that took the test better than you, but you were better than 80% of the people. And so when we look at this curve, that represents 100% of the people that took the test. So you can find yourself somewhere along that curve based upon everybody else. One more key thing here is that when we look at the normal distribution curve, the one thing we need to remember is that when we look at this guy right here, between 1 standard deviation below and 1 standard deviation above, that represents 68% of the people in the study. So let's just say, for example, that there was 100 people in the study. So if we take 68% of that, that means that 68 people would happen between those two spots. If you're 2 standard deviations, then that means that you're 95. So if you go down to 2 standard deviations below or 2 standard deviations above, that means between those two spots right there, once again, if we had 100 people in the sample, 95 people would fall between those two spots. So right now, that means that all we have left for that side and that side right there out of 100 people is only 5%. So when we break this guy down, we go 3 standard deviations. When we go 3 standard deviations, we'll come out here, go a little bit higher. That means between those two lines right there, we get 99.7% of the population. So out of 100 people, essentially we have all of them between 3 standard deviations. So there's going to be people greater than 3 or less than 3, but it's not going to happen very often. All right. Let's see, I think we got one more slide. Nope. That'll stop us. All right, so that takes a look at basically the properties of a standard normal distribution curve, just the basic understanding of what's going on when someone says to you normal distribution, when someone says bell curve. These are the properties that are going to apply.